The Transmitter.
This is Synaptic. Welcome. You have found our podcast that looks at the people, the research, and the challenges of the neuroscience space. You've joined us for episode 18. My name is Brady Huggett, and I host the show. Okay, today let's go back to 1967. That year, Fermilab, the premier particle physics laboratory of the United States, was founded in Batavia, Illinois, about 35 miles west of Chicago. The goal of the lab was, and is, to expand humankind's understanding of matter, energy, space, and time, and it is funded by the Department of Energy. It sits on 6,800 acres, has more than 2,000 employees, and every year more than 4,000 scientists from more than 50 countries visit Fermilab to use its accelerators, detectors, and computing capabilities. Now, since its inception, about 2,535 people have received their PhDs based on research done at Fermilab. But Timothy Ryan is not one of those people. That's our guest for today, Tim Ryan. Tim spent time at Fermilab in the early 1980s. He had wanted to pursue theoretical physics, but his instructors at McGill University had eventually advised him against it. He didn't really have the chops for it, as he says on this podcast. So he began contemplating experimental particle physics instead, and part of his thesis work at McGill was spending time at Fermilab. After his master's degree was done, he enrolled into a PhD program at Cornell, where the faculty expected him to continue to study particle physics. But when he arrived at Cornell, he told them he'd experienced a change of heart. The issue, as he says in this episode, was the long feedback loop in particle physics, the time between starting research and finding out what to do next. The project he'd worked on at Fermilab, for instance, had been funded a decade before anything was published. And during his time in Batavia, he had seen the very long time horizon that can be associated with massive collaborations. Now, those, of course, can bring giant payoffs, he said, but he did not think he'd find that timescale enjoyable. So he began to lean toward the neuroscience field. We talked about that on this podcast. We also talked about him studying under Webb, from whom he learned rigor of thinking and accuracy of measurement. And we talked about why he thinks he's currently doing the best science of his life. All of that coming up in the next hour. I recorded Tim on August 20th, 2024, a very pleasant day in Manhattan. Sunny, temperatures in the low 70s. We sat across the table in his office at Weill Cornell. Now, there was an air conditioning vent in the ceiling above us, blowing away. In fact, there was an AC vent on the ceiling in the backup room that we tried too. And there was no way to turn it off. So I've done what I can do to pull that out in post-production, but you can still hear a little wobble in the background. Okay, that should have you set up and ready to go. Here is your Synaptic podcast with guest Tim Ryan, starting right now. Okay, let's just see how we do here.
Okay.
So the first thing that I did want to ask you is, like, you've been at Weill Cornell, or Cornell, for decades.
There's two Cornells.
Yeah.
There's the one in Ithaca, which I did do my PhD on that campus, but they're relatively separate from this place. Financially, we're the same tip of the pyramid.
Yeah.
But after that, I mean, they've always wanted to have a closer association with us, but in reality, if you can have nothing to do with them, if you barely know they exist, or you could decide I want to partner with them. So it's not very hands-on.
It functions as like a learning capacity for Cornell. It's a learning hospital for Cornell.
Yeah, I think it started. I don't want to be quoted, over 125 years ago in the 1870s or 80s, and because Cornell realized that they couldn't have a teaching hospital in rural New York near Ithaca, there wasn't enough of a population base to sustain that. So that's when they decided they would do it in the city. and it never varied from that.
Okay, but I think I know that you were not born in New York. In fact, you may be, and I'm just guessing at this, you may have been born in Canada.
I was born in Canada.
And that's because McGill, that's why I'm thinking that.
Yes.
Yeah, where were you born?
I was born in Ottawa. I grew up in Ottawa, and I for the first 17 years of my life.
Yeah.
Yeah.
Okay, so how is it that your family was there?
Both parents emigrated there. My father moved to Canada from Ireland. He was born in most iconic. He was born in Tipperary and grew up in Limerick, and came to graduate school at McGill. In the late 40s, early 50s, just post-war era, to do a PhD in biochemistry. And then my mother was actually born in France, but to a Canadian father and an American mother. And her father was a scientist. He was an entomologist working on infestation and biological control. And he spent most of his early career in Europe. And she came over during the war as well.
Oh, so she was not also born in Canada?
No, born in south of France.
Oh, okay.
Yeah.
All right. So both your parents were immigrants.
Yes.
And they met each other.
They met each other, I believe, in Ottawa. Yeah.
Do you know how they met?
They were both academics. They both were professors.
Yeah.
I'm not exactly sure if that was, I think it was true when they met. And I think it was at some
conference.
No, it wasn't. There are no different fields. My mother was an English professor. My father was a biochemist. So it was something more ethnic. They were like some Irish embassy thing that my father got invited to through some other friend. And yeah, I actually don't remember quite the origin story of how they met, but I know it was at their social event.
But what was your French mother doing at the ethnic Irish meeting?
So although she was born in France and ultimately did her PhD in France, she was born a Canadian citizen because her father was actually a Canadian citizen and her mother was American. So she grew up speaking English. So but she did happen to learn French completely because of where she was born, and then ultimately had an affinity for going back to France. So.
Yeah. Okay. So your parents meet, get married, have children, all in Ottawa.
Yes.
And do you have siblings?
Two. I'm the youngest of three. I have an older brother and 4.5 years older, and a sister who's 2 years older.
So sometimes I ask this question about how, people get into a life of science, but in this case, it seems clear that you at least knew the sort of thing existed from your father's career.
I did. And my grandfather was relatively he was a bit of I was pretty young, so he loomed large in the sense that he was relatively famous. He had been elected a fellow of the Royal Society. He had sort of prominent positions within this field of biological control. And so science was always something that was talked about. And certainly my brother and I both sort of had liked talking about it and had an affinity for it. And my brother, being older, sort of paved the way, had chemistry sets first, this kind of thing. And, started going to science sort of lectures and things. So it was sort of baked into the way I was growing up.
So your grandfather, that was all in Ireland when he was doing this?
No, that was my mother's father. And so he did most of his work. So he was doing field work in the south of France, which is why my mother was born there.
I see. And
then was working in a lab in Cambridge, England for a lot of time. And he came here only after the war. He moved to Ottawa, actually, to take a job I think it was in a government association of dealing with biological control and infestation problems.
So your mother's father was a scientist.
Yes.
Your father's a scientist.
Yes.
In that way, your mother married her father.
I suppose you could say that.
Did you ever say that?
No.
With both your parents, I guess more on your father's side, was there a tie to Ireland for you? Were you going back to see family? And
not very often. It was. I was born in 1961, so travel was a little less common than it is now. I mean, it sort of was a wealth separator, basically. Now everyone travels, but then it was only if you had means. So we did go over as a family once when I was very young, and I went back again as just finishing college with a backpack.
Oh, you did?
And then I've only been back once since, which was last summer. I was at a conference in Dublin.
So you don't feel, sometimes people have this strong tie to that country. They go back a lot. That's not been your...
No, I feel tied to it only because I can imitate and understand Irish accents. I'm not fooled by Irish accents in the sense that I can understand them instantly. And
Yeah.
it must be that my father had a slight brogue that I didn't ever realize, but it sort of, my brain became wired this way. So, so I always enjoy meeting Irish people because it just makes me, I'm very familiar with it.
Yeah, it feels like family.
It does, yeah.
Yeah. Okay, so you have an older brother who's into science for sure.
Yeah.
Chemistry sets, etc. And so you're just sort of following along, doing those same things as your brother's doing?
Yeah, I would say that's, I think one was always excited by, we were all always excited, it seems, about learning ideas about how things worked in the world and what the principles were behind it. And so that's still true today. So I guess I was one of these people that pretty early on got a sense of how exciting the process of discovery was, and appreciated that. Learning about big discoveries, period. And even personally, just when you hear about them and you understand something, that's kind of your own discovery. Even if you're not making the discovery, it's your own discovery of something you didn't understand before. I always found very satisfying.
Right. So even if you didn't make the discovery, but you learn about it, it sort of lives in you as a new discovery.
Yeah.
Huh.
Yeah.
I never really thought of it that way. But yeah, it's so every time someone comes across that, it's a new discovery again for that person.
Right.
Now, your mother with the English history,
Yeah.
were you getting that side growing up as well? You know?
Yeah, always appreciated. She was a comparative literature professor. So there was always an appreciation for the humanities.
Yeah.
But I would say the science sort of dominated in sort of what we ended up thinking about.
She wasn't reading you literature before bed or anything like that? No, it was all science. Okay. Did you have other interests growing up? Did you think you wanted to be a scientist, or just, that's like the family tree?
The only thing I ever entertained, and I found architecture fascinating, mostly probably from purely the aesthetics. I realized I enjoyed certain forms of buildings and things and reading about it, but I don't think I ever had any, what I felt was an essential talent you probably needed for that, which was artistic skills. And so I sort of never came to me naturally, but that was the only other thing I sort of always entertained as something I found really quite appealing. It wasn't so much intellectually appealing as aesthetically pleasing.
Yeah, it didn't ping your curiosity in the same way. Like
Right,
how is that building made, or how is it?
No, not till much later.
Oh.
After I began to appreciate sort of physics and engineering, then it suddenly dawned on me, oh, these are actually interesting. Why does this bridge stand up?
Yeah, right. That's right. For hundreds of years or less. Okay. So anyway, you're moving through like high school. Did you do well in sciences in high school?
I did. Yeah. I went to, my parents ended up sending me to a French. So I grew up mostly speaking French in school, English at home, but it was a 100% immersion French school. For 10 years, I did that for sort of grade 1 through 10. Mostly my parents, as new immigrants, weren't thrilled with what they were sampling with my siblings in the local educational system. And they'd heard about this school that was essentially following the French government's curriculum for education. And it had teachers imported from France. It was really a French lycée. And we were sort of guinea pigs. That my brother was really a guinea pig. He went to the school when it had 2 years of classes, and they just added a year every year as they moved up. And I went in the first layer of expansion where they sort of doubled the size. They had 2 grade 1s coming in, but it was an interesting challenge because I distinctly remember the first day of class. I mean, they refused to speak English. I don't think they spoke much English, but they certainly refused to do it. So I spoke no French. So the first 6 months were, or 3 months probably, it was just like you had to figure it out. But 6-year-old brains can do this.
Right. So I guess if you wouldn't start someone I guess you could, but like in 8th grade, it had to be really young for just to drop you in like that. So that's also what your brother did?
Yes.
But you're the 3rd child. Yeah.
And they did not do it for reasons that never clear to me to my sister. They kept her in a different track, in a school, public school, or actually parochial school, I think she was in. And they kept her in that for a fairly long time. Well, with me, I only ever tried the one school. They just had me in this. And it was interesting because it certainly, you learned a different view of the world because it was all people from another country teaching you.
Yeah.
For example, our history curriculum in 9th grade was the French Revolution. Nothing else.
That's it.
That's it.
All year.
All year.
Wow.
So it's, this, you definitely have a different perspective. We actually had a separate history class for history of Canada because they felt like, oh, it's important. We are in this country to
Yeah.
learn the history. It was actually taught by a separate person, and it was a separate actual class. That
Yeah.
we did.
I mean, but these were not French Canadians? These are
No,
from
these
France.
were French. So the school had a mixture of a small number of people like myself, which would be called Anglophone,
Mhm.
native English speakers. I would say the majority were French Canadian families. And then because Ottawa is a capital, it hosts a lot of embassies.
Mm.
And so people associated with French-speaking country embassies, which
Would
there are
send their
plenty,
kids.
would send their kids there.
And for that, in that way, it's to keep French alive in their kids it's otherwise
Yes.
an English-speaking
Yeah.
country, right?
That's right.
But
Although it's officially a bilingual country.
every province is that way?
Federally, officially a bilingual country, but Ottawa being the capital and right on the border of Ontario and Quebec
Quebec, of course, right.
is very French. It's more French than most cities that aren't French cities.
Yeah. Okay. So this first 3 months or so,
Yeah.
I mean, obviously you still remember this, just like I didn't catch anything today. Going home the next day, I didn't really understand that. And eventually it starts to sink in.
Yeah, I don't actually really remember how I got through it. I do remember on the first day there was another Anglophone classmate, a 6-year-old girl who just stood up and cried the whole time.
Oh, man.
But eventually, I'm sure it was much faster than by Christmas. It must have been a relatively quick thing where you pick it up. I mean, I'm not the first experiment this is done on.
No. And I guess because they're also teaching you, things like the alphabet in first grade.
Yes.
So that's perfect for learning
Yeah.
languages anyway. Do you still speak French? Is that?
I do. It's interesting when I'm very comfortable speaking French, although what you lose is vocabulary that you don't use anymore. And another fascinating thing about the brain is when I go to France, and if I'm there for just a few days or more, suddenly words start coming back to me that I'd forgotten. I mean, they're like, oh, I know that word. Like, I won't even be thinking about it. They just somehow unlock this like special part of my brain, and now it's accessible again. Whereas right now, I might struggle to think of the word for
Right.
monkey wrench or
Right. Have you looked at that at all in your work?
No, I've not.
That's fascinating though, right?
I do find it fascinating. There's many features like this shows you how humbled we are about the brain, about these fundamental things that we don't understand. I mean, another example, I find it motivating. It's not the scale that I work on, but if you learn to play an instrument at all as a kid, maybe you do it like I took piano like many for 5 or 6 years and
Yeah.
then got too busy.
Yeah.
But I could still if I sat down at a piano for more than 10 minutes, suddenly, like I remember this happened to me as an adult where I sort of tried to play again a little bit more regularly. Suddenly, like it's as if someone downloaded a program and I was playing this, like I didn't know where this came from. Like there was some stored muscle memory, but from decades ago
Yeah.
that I unlocked. And
But it almost feels like everything in your life is in there
Yeah.
someplace, but we just can't access it.
Right. Yeah,
Yeah.
exactly. So I find it humbling that, there's a lot to understand about the brain. But that being said, my work doesn't try to approach that
Yeah.
problem. So.
Yeah. Okay. So, you're finishing this. So for 12 years.
I actually only did 10. So the school was accelerated as well.
Oh, okay.
Not on purpose. They just ended up being accelerated. And I left after 10th grade and went to university.
So at 16.
Yeah.
Oh, okay. And the whole thing was French immersion.
Yes.
Okay. And then you went to McGill.
I did 1 year at the local University of Ottawa. And that was already that was my first instruction in English other than an English class. And so there was mixed. I had both because it was a bilingual university. I had some of it in French, some of it in English. And I did that for 1 year. And then I decided to transfer to McGill.
So this first year where it's just English, did you find that odd?
No, it wasn't.
No
it's my
problem.
native language.
Yeah,
so.
it wasn't a problem. Okay, so can you tell me why you started at that school and then transferred? Were you aiming for McGill? And
I don't know. It's a good question. I found it pretty easy, even though I had jumped in fairly young.
Was that part of it? It was the reason you didn't go for McGill is you're like, I'm only 16.
No, I didn't even think of it then. I think it was purely social. So I wasn't the only. This school was accelerated, and a handful of us, my friends, I wouldn't have done it if I didn't have peers doing it, I'm sure, at 16. So a bunch of us left all at the same time, realized that this university would let us in because this school was on a faster pace.
Yeah.
So there were a handful of us, 6 or 7, that all went into the same first year at the same time. And so I think I wouldn't have done it, I think, without sort of peer support. So I wasn't thinking of like at 16 going off to another city. But after a year, I did find that, it was, I found it was interesting. My brother had gone to that school for 4 years. He was in his senior year when I was beginning, I guess, or something. So I don't know, I just, somehow my eyes began to open up and I thought maybe it'd be interesting to go somewhere else.
This French school, back to this, it was not designed to end at 16.
No, it had 2 more years.
Oh, but at 16 you realized you'd like learned enough to be on a college track.
Yeah,
obviously,
I knew I could get into college because
your friends were doing it.
Yeah, it had happened a year before. Not nearly as many, but the sort of floodgates opened. It's like, oh yeah, we have learned enough to basically, we could skip 2 years right away.
Huh. Yeah. I'm not sure I would have wanted to do that at 16.
Yeah, it's a good question. I, as I said, I wouldn't have done it without peers doing it. So in some ways, it didn't feel quite as foreign. And I still lived at home, so it wasn't
right. Yeah.
The real college experience. The other thing in Canada, the college experience didn't used to be the same as I've come to learn it is here, which is, it's such a big thing in the American culture, the college experience.
Right.
It's been advertised, movies are made.
Right.
And so much focus is made on, you want to optimize this thing. It may be the peak of your life might happen there.
Right. You're away from your parents. You're still young. You're living in a dorm with other people. They might be crazy, whatever, like a party
But in
scene.
Canada, most people simply go to the college in the town they live in.
Huh.
And sometimes, and you typically don't. So when I went to McGill, all of my classmates lived at home practically. They were all Montrealers.
So there's not that.
Now I did live in a dorm, and there obviously were dorms because there were people that came from all over the world and all over Canada. But mostly the schools tended to rely on local populations.
Huh. Okay, so at 17, you decide, it's not that the school that you were at was poor or anything like that, but you thought, I'm not being challenged enough. I want to go to McGill.
It was a mixture of things. My father had done his PhD there.
Oh, okay.
I sort of knew about Montreal, and I don't know, sometime I got a bee in my bonnet one day, and I wrote for the booklet, which there was no online presence then. And I got sent a course catalog, and that's what you looked at. And I was like, oh, look at these exciting classes. And I decided, oh, this might be. And I talked to my parents, and my dad they're both quite supportive of it. They thought, this, obviously he had come and gone to McGill and thought highly of it. So they didn't see any reason that this would be a problem. So
you probably will not remember this, but do you know what courses you saw that you thought, oh, I want to take that?
Yeah, I went straight into honors physics. And so that was McGill adhered a little bit more closely to the British educational system of being highly focused. They assumed that when you were a high school student, you got a well-rounded education. And then by the time you got to college, you focused. I would say in America, especially at liberal arts colleges, it's meant to be broad right through, or Columbia or Chicago. There's very core curriculum type of things. This was not. So I just saw this exciting looking, challenging program in physics. So that's what got my eye.
Okay. So actually I saw this in some of your background that you did study physics first.
Yes.
In the classic sense.
In the classic sense, yeah.
So that was the main thing that you were curious about. How do things work? What is force? What is mass?
Everything. And you sort of get this, the people who I found that are attracted to physics is they're really trying to understand how things work.
Yeah.
And then you realize that you can get more and more fundamental with it. So it started out with sort of Newtonian things, which were figured out in the 17th century. Then you learn about electricity and magnetism from the 18th century. And then slowly, this next, like the quantum era, which was sort of, even though it was the beginning of the 20th century, it was still quite modern feeling because it's how devices work and lasers and all these things. So it definitely felt like this was the frontier. And it felt like that's where all the exciting discoveries are going to happen.
Okay. This is fascinating because, all right. So you finished your undergrad at McGill.
Yes.
And I think you stayed for a master's in physics too, right?
I did.
And what area of physics were you looking at specifically?
There I worked in high energy particle physics, which, so in all honesty, when you're an undergraduate in physics, you become good at doing problem sets. That's how you learn, right?
Yeah.
You're given a lot of homework, a lot of problems, a fair amount of math, and you solve these more and more challenging problems. And that's what so you sort of have this impression like, this is physics. It's like doing this kind of more theoretical work. And I thought that's what I wanted to do, was to try and do theoretical physics, only really to come to the harsh realization that I didn't really have the chops to make it in theoretical physics. Very few do. I mean, plenty do, but I was not one of them.
Yeah.
But I still love physics. So I thought, this is still a fundamental area. So I joined a group that was in experimental particle physics. So that was a circuit where those, it was interesting because I got to experience other things. Even at that time, particle physics only happened at large centers. It's much smaller scale than today, but it was still large scale compared to anything that existed. So the groups might have been 25 to 40 people from all over the world, that came to work together. And there were different universities, and different universities were sort of in charge of different aspects of the experiment. And so I just got tacked on as a master's student to sort of as a helper.
I see. Okay. But so at that point, especially when you're chasing this master's, what did you think your career might be?
I probably assumed I would head towards academic physics,
but not on the theoretical side.
No. Then I sort of, once I sort of came to this disappointing acceptance that I was not cut out for doing theoretical physics as a profession. I would explore whether I was cut out for doing experimental physics.
How did you know? Was there one moment where, I don't know, you went into a course and you took your first test and you thought, whoa, this is beyond me? How did you know that you were not cut out to be a theoretical physicist?
I went to talk to faculty, and they made it clear.
Which
is very tough. I mean,
you said, I'm thinking about this for a career, and they said, you should think about something else, Tim.
Yeah. I don't remember the exact words, but it was more or less along that line.
Yeah, that does sound.
And, I give them full respect. They did what they were supposed to do.
Right. Did they push you in any new angle? Like you might be good at that? No.
No, they didn't. No, it wasn't a counseling session.
Yeah. It was more direct than that. Okay. So then you get your master's in McGill, and then you have to make some decisions, right? Like
there's an important part about McGill's, during that time, I was doing my thesis work there, but because it was work in an international group, the center of the work was actually at Fermilab in Batavia, Illinois, which was, at the time, the center of experimental particle physics in the United States. The only counterpart was CERN in Switzerland.
Yeah.
And so it was sort of exciting because now it's a national lab. It's thousands of physicists gathered from all over the world. You feel like, you're surrounded by these big machines. And so that part was very exciting to get a flavor of this, even though the part we're playing is really a tiny cog and something. But it was, and I also even got to go to SLACS, the Stanford Linear Accelerator, and connected to the Stanford campus right under 280.
Yeah.
And so that was also exciting because I got to sample it there. But what I took away from this is that I still like particle physics, and I thought I will try and continue in this. But one thing I don't want to do is have to live in Batavia, Illinois.
Yeah.
Because it really was isolated.
Yeah.
And for a student, it's exciting in lots of ways, but not in lots of many other ways. I said, only want to go to a place where I could do this on campus.
And you were probably 20 at that point.
Yeah.
Yeah. So I understand. Yeah.
And so that sort of narrowed down what my choices would be going for the next stage. And so one of the places I applied was Cornell because they had their own synchrotron. And so I said, well, I'll look at only places where you could do it locally. And that narrowed it down to Stanford or Cornell, basically, where those would be viable. And I chose to go to Cornell. But by the time I got there, I had also changed my mind about particle physics.
All right, that's what I want to get at. So you enrolled in this PhD program, I think, right?
Yes.
You got another master's, but you were there for the PhD program.
At Cornell.
Yes, at Cornell. Right. But so you went in thinking that, okay, I'm not going to be a particle physicist.
Yeah. By the time I got there, but basically, by the time when you apply, I was still thinking it must have been fall of the previous year. I was thinking this is what I want to do. But now comes spring when I open the letter, I've been accepted, and I decide, okay, I'll go there. I was immediately assigned some person in particle physics as my graduate advisor. But as soon as I got there, I was made it clear I sort of had a change of heart. They're very open. I mean, it wasn't.
Yeah.
It's a graduate program.
Yeah.
It's a big graduate program. I had 45 classmates all going in to a PhD in physics.
Yeah.
But the other thing, it was a bit of a safety valve. The reason I didn't go in completely blinded, I noticed that Cornell did have a pretty rich spectrum of physics going on across the board. So not only did it have its own particle physics thing where some of it was local, but it also had strengths in many other areas. So that's why I felt I'll find something.
What was the thing that, in between that fall and the spring, what happened where you decided, no, that's not going to be my focus?
It's I realized one thing I was missing, and I probably had not yet experienced it truthfully in any scientific endeavor, but I felt like the feedback loop between working and finding a result and then making a decision about what to do next, that was a 10-year time span in particle physics. Because the project I worked on had the grant proposal was put in, let's just say it was 1977, and that team was funded worldwide, a team assembled. I participated for a couple of years right in the middle. The big papers that came out of that were published in 1987.
Yeah.
So it was a very long time horizon to pull off these sort of scales of work. That's still true.
Yeah.
And there can be giant payoffs. The incredible discoveries. I still follow it. I mean, still find it fascinating. But to me, that time scale was too slow for any kind of satisfactory feedback loop. That I figured something out. It's like this is what we'll try next. So that was missing for me, which I find that a little bit too frustrating. That it was a bit more like I have a job to play. It's a kind of an engineering role. Like, we're going to be analyzing this, and it's going to be fed up. It'll be plugged in places.
Yeah.
And I just realized that I wouldn't find that enjoyable.
So when you say feedback loop, do you mean that you would do your work, and because you're this cog in this mighty machine, you wouldn't know if the work was good? You wouldn't get feedback saying, "That's a great job, Tim, keep going," or you're saying that when you start to get results, it would take you 10 years before you'd know what the next step was?
It was more that. Yeah.
It's kind of almost like the impatience of it, of having to do a 10-year project.
Yeah. And I realize, some people luckily have the patience for it, because it's still a very important endeavor about understanding the world we live in.
Yeah.
But that was another way I realized I wasn't cut out for it for other reasons.
Yeah. So then I think your advisor for this program ends up being Webb?
Yes.
So did you identify him?
Pretty early on, yeah. He was a bit of a polymath. He had worked in all kinds of areas of physics, and it's funny, I had a taste, very indirect. I took almost no biology.
Yeah.
I took one required class at McGill. I hated it.
Why?
I felt it was everything I didn't like about science. What I liked about science was like the work of doing problem sets was figuring something out. And the biology really, at the introductory level, was, this is how things work. This is the way we understand it now. And you are going to be tested on whether or not you know what
whether
we
you've
know,
ingested this and retained it. Yeah.
And so it's the only time I ever took a multiple choice exam.
Oh, really?
Yeah.
Oh, wow. It's so funny. But you didn't, you said earlier that you had this curiosity about the way things work. Like, biology does feed into that.
Absolutely.
Here's the way your
and I
body
was
works.
extremely curious, very ignorant, because I didn't really take it for very much. And it was also a survey, broad biology class.
Yeah. 100 students in the class, kind of thing.
Hundreds, and it covered botany to everything. So I really did not get very much out of it. There were interesting things, but I was sort of too embedded in something else. But I had friends I had a friend working more closely to neuroscience, and I would just learn about it from him. And I realized, it's fascinating things that are, the way a lot of people are attracted into neuroscience because of psychology
or the brain.
We're all curious about how we work.
Yeah.
And so I found this fascinating, and what Webb had nothing extremely direct at the time, but sort of, he had written some things was showing like some interest in these problems and why studying these very fundamental things might have impact on it. And so that's the first time I went to talk to him was a little bit because of that, just because something he had written in one paper or something on some blurb about his lab caught my attention.
But so you're saying he was also sort of multidisciplinary in that way. So he had some physics, obviously. He also had some biology in there. He had done, so he was at the time he was chairman of applied and engineering physics. Okay. He had its own very interesting route into that field, but he had made many as a master at developing and applying sort of advanced techniques of how to analyze data
from really that ended up being important in both chemistry and biology, even though it was really because he was a physicist that he could do it.
Yeah.
I used to call it applied statistical mechanics, because that he was really very adept at looking at statistical systems and ensembles and seeing how you could extract new information with novel kinds of measurements. And it turns out that ended up being a really useful thing for biology eventually. And so he had sort of marched through, and some of the times he thought, well, we can make an impact on this biological problem. So he would go into it, both feet.
So when you came to him and said, I'm thinking about maybe can I work with you? I came for this program, but I want to focus on something different. And you didn't have any bio other than this one course. Was that a problem, or what did he say?
No, he was pretty used to this kind of background coming in, being in a physics, and half his students were either getting their PhDs in applied physics, or half of them were getting them in straight physics.
Okay.
So it wasn't unusual. He just says, oh, if you're interested in this, I suggest you take this class or audit this class, and they would be outside of physics.
So what did you learn working with him? This feels like the big shift in your career.
It was the big shift.
Yeah. So what was he showing you? When did you start to think, okay, I'm really going to start to focus on straight neuroscience?
Oh, it wasn't that time, because I did not do that while I was a PhD student. I still worked. Although I worked on things that were sort of biological problems, it was really still using a lot of physics to study things. What I really learned from him was rigor of thinking and accuracy of measurement. I've ever lots of these. He was very challenging. He would challenge your thinking. You would try and explain something to him, and he would find all the flaws that you didn't realize you weren't thinking about this rigorously. And so it could be a bit scary. He was, but for some, quite a scary personality, I suppose. But, that was a real trial by fire in some ways. I felt like, that's when I really began to appreciate. I realized he was complaining like we had not measured something well enough. And I didn't see the relevance of it. I really thought, why waste my time? And he was adamant. And, so probably a year later, I realized, oh yeah, he was really, right. He knew what he was talking about. We should have made that measurement, right? And it's part of the practice of becoming a scientist in lots of ways. There's probably 1,000 versions of this arc.
So when you say he was scary, meaning that he would just approach you and say, that's wrong, do it this way. Yeah. And that some students didn't
hold
appreciate
back,
that.
No.
Yeah. But you didn't have a problem with that.
No, I guess I had a tough enough skin at the time.
Yeah.
There was a full spectrum of personalities in physics. There were 45 students who were accepted which is a pretty large graduate class. I'm sure they're not that size anymore. And I remember, I think 30 of us probably felt that they had, because it was 50% larger than normal. And I think at least 3/4 of us thought that we were in the 50% extra that they didn't normally let in.
You're like, I'm the weak link. We're the weak links. So you stayed there, I think 5 years or something in the PhD program. And then you did a postdoc.
Yes.
So go ahead.
Right. So it was during that period I began to get a little bit more exposure to biological sciences and what the problems were. And even then, though, I'll tell you that there was a memorial symposium for Webb. He passed away a handful of years
2020 or something. Yeah.
And 2 years ago, there was a memorial symposium in Ithaca that I was invited to, and I spoke at and was seeing a bunch of people. And I remember, because then it was he had a very long career covering all kinds of things. And I remember, advertising the reason I chose even what I work on today. The origin was a paper he handed to us all, probably a paper from around 1982. It was actually an internal preprint. There was no preprint servers even for physics then. It was from Bell Labs, and it was from a former student of his who became a very famous neuroscientist, David Tank. But he had just sent along some papers that they were working on, and it was a purely theoretical paper about neural networks. And it was from Tank and a guy named John Hopfield. And it was sort of foundational paper. But I read this and I just found it, I was transformed, because it was so simple. What the paper ultimately showed was that you could wire up a set of op-amps in some ways and give them really simple properties. And all that mattered is the weights of how well the output of one op-amp influenced the input of another one would be predictive of certain properties of the network that could be used to do useful computations. And they built devices like this. And this was the Hopfield network. And the parameters that you could tune were the synaptic weights. And that's what I realized. Oh, no, synapses. I sort of went whole. I said, oh, yeah, synapses are probably the be all and end all of ultimately controlling what you can do with the brain.
Yeah.
And so even though I didn't work on them at the least bit as a graduate student, the seed was planted then, realizing, oh, this is a piece of biology that's going to be fundamental to understanding in neuroscience.
Well, you were right about that for sure.
And basically that's when I left to do a postdoc then at Stanford, that's when I decided to jump in. I wanted to work on synapses.
Oh, right. So then your postdoc is like cellular and molecular physiology or something.
Yes. Yeah.
So that's when I was looking at your background, I thought this was the big shift for you. But you're saying no, actually, maybe the PhD.
It happened. I became sensitized during the PhD, but it's true. The real shift was then I had to go outside of my comfort zone completely, and I joined a lab, not really knowing what I was going to do. I happened to join a lab that also wasn't giving tons of direction, for better or worse, but mostly discussing ideas. I came up with some things that I thought were interesting. Truthfully, they weren't related to synapses. I was sort of holding off until I saw that opportunity, and sort of basically futzed around for the first year or so, and then landed upon something where I could use my skills. And it turns out I could work on synapses, and that was the turning point. So probably 1992 even is roughly when that happened.
So this was with Stephen Smith.
Yes.
Yeah. So not to was he not giving direction? It was kind of a free flowing lab.
It was pretty free flowing. Stephen is honestly a visionary person, but because he's wired this way, he gets extremely enthusiastic about fundamental ideas that he likes, and he tends to spread himself around these areas.
Yeah.
And so, for him, it's been a very satisfying career to sort of move from sort of exciting thing to exciting thing and seeing what they can contribute. For the people that train with them, it depends on how it goes. So with mine, it wasn't really, the thing that I ended up locking on, I have to say, was not really directed by Stephen. He was fully supportive of it. I mean, Stephen can tell when something, I remember when I was working with someone who actually had come on sabbatical to Stanford, and it was a well-established scientist, and we ended up working on this. It was a technique to use fluorescent dyes to label synapses. It's kind of for not the very first time, but one of the first times. And I realized we could exploit this and learn lots of new things. And I remember once we had a data set analyzed, and I was showing, it was sort of over Christmas this year, and I was showing Stephen it, and Stephen, he nailed it, because what he said was, this is going to change what you do. Like he could see like this was going to be a big deal, and this is going to change what you do.
What part was going to change it?
Well, just when he saw that, like the potential that we sort of tapped into being able to visualize synapses and study their properties in ways that had never been done before.
By using dye.
By using just dyes. He said, this is going to change how you're going to do things and how many people will do things. He sort of had this inkling that was, and he's right in lots of ways. He was right.
Yeah. Okay, so I think, no, tell me if I'm wrong, but it's like 97 you finished that or something, and then it was time to get like a job.
Yeah, time to get a job.
And then you came here.
I came here.
Yeah, so this was like an assistant professor or something.
Assistant professor, in a brand new, a department that was being rejuvenated because it had essentially mostly died off, and a new chairman had been hired, who was someone who I had met. His name is Fred Maxfield. He's still here. He's no longer the chairman, but it's funny how close these circles are. When I was a graduate student, Webb had applied for major funding from the government to make his lab a national resource center, which amazingly with the goal of not providing a service to anybody, but just to fund the discoveries that his lab is good at doing. Yeah. And he convinced people to do this. Wow. But one of the site visitors to come and review this was Stephen Smith. And another one was Fred Maxfield. Okay. And so they were both there. And of course, this was a session where the students, a handful of students, are giving talks to this panel of experts about this is what Webb Labs does. Yeah. Right. And it's kind of odd that I realized that both there were two people that changed the course of my career that were both there to show you, like, well, you never know
they were in the
who's
room.
going to be listening.
Yeah. Did you talk at that?
I did.
Well, it must have gone well then.
They got the center. Yeah. It went well.
Yeah. Okay. So when you come here, not long after, in like 2000, you win the McKnight Technological Innovations in Neuroscience Award, right? Yep. And this was for, I think, what you're just talking about, ways to better monitor what's happening at the synapse.
Yes.
Yeah.
Yeah.
I mean, I had not heard of that award, honestly, till I saw that you won it. But what was the, what did that do for your career other than some funding, obviously?
Yeah, the funding was probably less important, honestly, because it's still an early phase where I'm living off startup funds. And honestly, in that era also, I had managed to get an NIH grant the first crack. So I was sort of off and running. But these are more what it's joked about as sort of the Young Turk Awards. Like you want to try and get into these networks of people. So it was before networks were known to be truly a thing that all these places want to build, right, on purpose for young people.
You mean universities, academic centers.
Funny, like Simons,
Chen
Zuckerberg. They're all about making these networks for the benefit of science, right? But you realize when you get this, you go to their meeting, you're meeting sort of the who's who of people in science.
Yep.
And you get to hear about interesting ideas.
And then you win it again 10 years later.
Yes.
Right. And I mean, I know that data is a little like we're using data a little bit too much maybe in reporting or certainly maybe sports reporting, but like you're the first person to ever win that twice.
Probably, yeah.
Or at the time that was true. Maybe it's still true. I don't know.
No, the award doesn't even exist anymore.
Oh, so then, so the door's closed on that. Yes. You're the only one. But this time it was to look at ATP.
Yes.
And you were going to use luciferase, I think, for this, and which comes from fireflies.
Yes.
But I don't know if you bioengineered that, or is that naturally the way that, so luciferase lights up when it is in contact with ATP in the firefly itself, or did you have to bioengineer it?
So we didn't have, it wasn't that heroic. I'll give you a bit of the background. So truthfully, the idea for ATP was not well grounded. I mean, in the sense that literally was the feeling, this might be a cool thing to measure. So this is sort of my roots of Webb. You don't necessarily know what you're going to learn.
Yeah.
But the motive is, let's figure out how to make a better measurement.
Yeah.
Then we'll see. Because the history of physics has taught us that the basis of discovery is in better measurements. So that's sort of rooted in me. It's what I breathe. And I sort of believe this is always something that's going to be useful if you do it well.
Yeah.
If you do it sloppily, you won't learn much. And so that was all it was. And I was thinking about it. It's like, I wonder, and I knew luciferase was a tool that had been used because in a test tube, all it takes is ATP and a small molecule called luciferin, and it glows. And it had been used as a reporter gene in a variety of systems because you can make things glow like this. But no one had really tried to use it in a quantitative way. And I reasoned, maybe we could stick this into synapses and watch them glow and figure out a clever way to calibrate it so we could tell how much ATP was there to drive this reaction.
So it was known that ATP was there at the synapse.
Yes.
But what you wanted to do was to figure out exactly how much, when it was used, et cetera, like better monitoring for what was happening there.
That's exactly right. Yeah.
And so I think what happens is this paper that comes out in Cell in 2014 that shows not only is ATP present, but it is locally synthesized, right?
Yes, that's right.
And that I think was the first.
I think so, yeah.
Yeah. To me, that was, I mean, I read the paper and I was like, that's super, super interesting. I'd never considered it, but like once you read it, you're like, of course.
Yeah, no, I think that there was certainly an appreciation that all cells, in some ways, the definition of a living cell is a cell that can make ATP.
Yeah.
Because that's what sustains the life of the cell. So maybe it's circular in the end, how you want to define a living cell. So neurons for sure have to make, all living things make ATP. I think what is often not appreciated about the architecture, I like to think of neurons, they're very specialized because I think of them as a sort of biology at the extreme, because there's no bigger cell in our body really than, maybe exceptions, but individual neurons can cover enormous distance scales. It's now known even in a mouse brain, forget about the spinal cord, a single axon might cover tens of centimeters, right? Even in the cortex, even much more than the linear dimension of the mouse, right?
Yeah.
And so everything is happening very far away. Our classical biochemistry has all come from studying sort of muscle, the biochemistry of ATP synthesis. A lot of it came from studying pigeon muscle. So this is not nearly as, it's got its own complexities in architecture, but it's all relatively compact. So it's full of all this machinery. So neurons have this other problem with, like, they have to ship things really far away, right? And so the rules are going to be interesting and different, and create different opportunities and vulnerabilities. So I also find that sort of interesting. And another reason why making measurements of things out there, we might learn things that we're not expecting.
First off, like I just want to say, like you were talking earlier about how when a discovery happens, then you learn about the discovery. It's like when I read that paper, I was like, oh, it never occurred to me. I think I was like telling my wife about it, right? Because it has a sense of discovery. Like I just figured out what's happening and why ATP is necessary. So I thought it was just a fascinating paper. But that, I think, seems to have set your career on a new trajectory.
It has,
for sure. Can you tell me what that meant? I mean, it's still, I think, your most cited paper, number one, yeah?
Yep. Having an impactful paper probably makes people think, give you more of the benefit of the doubt when it comes to...
And your next paper?
Your next paper, or scoring a grant or these kinds of things.
Right.
So those are tangible things that you're not in the room when it happens, when they make decisions, but people did, it got appreciation. Certainly that's true. To me, more, and it's nice. Our egos all like being validated. There's no question. We're all human, but what it did was open up a door to new interesting questions, because knowing that it was important, it had to be made locally, then said, well, how does that all work? And I would say in parallel to that discovery, another part of that paper, which we had actually made before we understood the role of the ATP, was we recognized also that synapses are incredibly sensitive to the need to make ATP on demand. And if you don't let them do it, they collapse really quickly. So I realized that was probably extremely important property of synapses that we need to worry about.
So why is it important to be able to make ATP on demand? And I think this has to do with vesicle recycling. Is that right?
Yes. Yeah. We discovered through our work that the first thing that seems to break if you don't have enough ATP is the process of recapturing the proteins of a synaptic vesicle after it releases its neurotransmitter, because it's fused through a process called exocytosis. Mm-hmm. Those things all have to be recaptured so you can remake the vesicle, and that is the process that breaks when you don't have enough ATP. And that, of course, means you will run out of vesicles. When you run out of vesicles, you will no longer be secreting neurotransmitter. Which
means it may lead to disease.
Yes.
Right. So that I think like the first thing people thought about, maybe that's not true, but it was like Parkinson's.
That is the direction we currently are working on really heavily.
Yeah.
Yeah.
So I think so. You have a grant. You have a couple from NINDS now.
Yeah.
One extends to next year, and one extends to like 2029.
Yeah.
And you have some Michael J. Fox funding as well. So obviously that's Parkinson's. But you said before, like when you're in that room and people are looking at your grants, that stuff is probably you're awarded those grants based on this work. And has it become easier for you to win grants now than back in 2001?
No, I don't think so.
Huh.
No, I don't think so. I mean, you're only given so much credit for retrospective contribution. It's mostly about what are you proposing to do. That's really what's evaluated. They're not gold stars. They're literally say, what are you proposing? And then you're competing with a bunch of other people with good ideas as well.
But in this case, you're able to say, look, we did this, and we're pushing it in this direction.
Yeah, it certainly helps. It's a bit hard to answer that question fairly, because whether it's easy or not, I mean, I've had a typical career. I've been luckily able to sustain continuous funding, not without rejections.
Yeah.
So they still happen, but I feel more confident that like the work is so interesting, and it's led us to make discovery after discovery.
Yeah.
That's what I feel to me has been impactful. So it's just kept it incredibly exciting the whole time, including today. It's still as exciting as it's ever been. So
you're also, I think, associated with Janelia.
Yes.
Somehow. And I think that maybe started in 2018 or something like that.
Yeah.
So tell me what you're working on now.
Okay. So because of the discoveries we made about the importance of ATP, I became interested in where this impacts neuroscience.
Yeah.
Right? And so there's two flavors, one of which we're not working on, but it's a good story to convince public. So there's a paper that was published about 25 years ago. It's a human psychology experiment in some ways. It's just take a room full of people, divide it into two groups, give half the group an oral dose of artificial sweetener, aspartame, and give the other half the group an oral dose of glucose. Then give them a list of 25 words and test their recall on various timescales. The conclusion is the people that got glucose did twice as well as the people that got aspartame.
And did they switch them?
No. No, it was just,
Okay.
it wasn't meant for more complicated than that.
Yeah.
Right? And so, and of course, we've all experienced this. I'm sure you've had a snack that's improved your ability to focus and
Yes.
edit your podcasts.
Yeah. Yeah.
And so that was a realization. Reading this is, our synaptic. It doesn't have to be synaptic performance, but given how sensitive synaptic performance is to fuel availability, the implication is that we're actually not running at optimum a lot of the time, which is not something I would say most people appreciate. But on the other hand, it's hard to this data is so simple.
Yeah.
And there's probably evolutionary reasons for why. I mean, we weren't perfected.
Yeah, right.
There's some headroom to get better.
Right.
There's also a lot of room to get worse. So I use this in a lot of my public talks and things because it's easy to convince people like there's an angle we're not thinking about. Then I bring them into like synapses are sensitive to this. But the flip side is then we also know that as we age, our fuel delivery systems to the brain get worse. They get worse to the whole body.
Yeah.
Actually, not just. That's why elite athletes stop being elite athletes, as for lots of reasons with age. But one of them is that they're not able to deliver fuel and oxygen as efficiently as they were when they were 25.
Yeah.
Now, Parkinson's was. I'll tell you the honest truth. I was having lunch about 4 years ago with a colleague at Rockefeller, and this is the importance of networks. And I was telling a little bit some interesting things, and we had some ideas about Parkinson's, about why the neurons that die in Parkinson's might be particularly vulnerable because we had thought we'd figured out that they might be there's a reason they might be consuming way more ATP than most other neurons, and that was sort of a hypothesis at the time. Mm-hmm. One we're still testing actually to this day, but like a couple of weeks later, I ran into him and he says, I just heard this interesting talk. You might want to look this up, and he didn't really recall too much. I mean, he gave me the name of the person, and I went and read this paper. It was a study starting with a paper 10 years ago where a group had decided to see if they could keep flies from dying from a genetic perturbation. The genetic perturbation was to turn on a cell death pathway. And the experiment was feed the flies drugs that humans take. So FDA approved drug panel. Right?
What drugs?
In principle, you would like to do everything. In practice, that's a couple of thousand, and you don't inject drugs into flies. You put it in their food, so it's very inefficient. So everything was expensive and laborious. So they cherry picked a couple of dozen for reasons that are too complicated and not worth going into. But amazingly, they found a drug that seemed to double survival. So that was then they tried to track this down, and it didn't make any sense. The known target for the drug, the reason it's used clinically, was an adenosine, an adrenergic receptor, not adenosine, an adrenergic receptor. And it's only used for one clinical indication largely, which was because this receptor happens to be in the endothelia that line the urinary tract. If you're having trouble with urination because you've had something impeding the flow, like a growing prostate, this is meant to relieve that symptom. It's a local blood pressure drug. Okay, so if you fast forward, say, well, it doesn't seem like, what would this have to do with, and it's a fly that don't even have epinephrine, for example. Right? Yeah. They tracked down, they realized it's probably not that target. And they did other biochemical experiments. They went fishing, and what they did, the hit they got was the first ATP producing enzyme in glycolysis. And they thought that the drug did not inhibit it, but actually made it slightly better. And so they had other types of measurements, again, a bit crude, grinding up flies, measuring ATP and pyruvate when the flies were on the drug from the brain. All look like, it looks like it's making things a little bit better. And then you fast forward a few years, they made a slightly bigger team, or they teamed up with other people, and they tested this in Parkinson's models in mice, flies, and rats. And amazingly, the drug was incredibly protective now in all these cases. And so I saw this and I was really excited because I was already thinking there was a bioenergetic root of maybe Parkinson's, but no data. I just literally had some hand-waving reasons why I thought this. And I said, this really looks like something. And I said, I wondered if this is related to the fact that when we had looked explicitly at Parkinson's mutants, not looking at ATP, we had blinders on. We were looking just at what was it doing to synapse function, vesicle recycling. And we noticed a bunch of these different known Parkinson's mutations seemed to slow vesicle. They slowed it down. Oddly enough, metabolic problems slow it down too.
Mm.
But I had not made the connection until I'd read their paper going, oh, I wonder if it's all bioenergetic and this is at the root. So a subgroup of the people that were participating in that paper published in 2019, now they had looked a little bit at humans in this paper, but they did a more serious look back and said, listen, there's a bunch of data from people taking this drug. You can do what's called a retrospective analysis. Yeah. And the conclusion was, and this was published 2 years ago by a group of epidemiologists and quite a famous scientist named Mike Welsh, who is responsible for, in my opinion, at least in part, for the reason cystic fibrosis patients are living 2 decades longer. It's because of fundamental work he did in the 90s. He happened to be participating in this. And they showed that men taking this drug reduced the likelihood of getting Parkinson's by 37%, which is the biggest effect ever claimed for neurodegeneration.
Yeah.
And so it's all incredibly exciting. But I thought one of the weaknesses of it all, and then I realized why drug companies, I don't have a full analysis of what their interest level is or was. But one, of course, it's a known generic drug now. The other is the data that it was really working on this enzyme is the weakest. Because if you say, what's the gold standard? Purify this enzyme in a test tube, measure the enzymatic activity and add the drug, and how much does it make it work better?
Yeah.
And that was a very small effect, like a few percent. So then it's like, that's a bit of a cross your fingers that's really the target, because we're not saying the drug doesn't protect against Parkinson's, but is the drug really doing it by this bioenergetic problem and really via this enzyme? And so we set out in the last few years to determine whether this holds water at the level of, is this enzyme really that key in this problem? And is the drug acting like the enzyme, like there's more enzyme there or not? And so I'm happy to say that paper is coming out in the press 2 days from now.
Oh, God. Okay.
And basically everything that came before us seems to hold true. We even did experiments where we just sort of did a gene therapy version in a mouse where you use a virus to deliver this enzyme. The enzyme is called phosphoglycerate kinase 1. And we just have the striatal neurons in the midbrain express more of this. And it really is strongly protective against the kinds of lesions people use in experimental Parkinsonism.
The thing that's made me think of, and it's sort of related, but so there's a certain percentage of cases of ALS that are genetic.
Yeah.
That's known. But the rest are spontaneously arising.
Yeah.
And maybe it's something like this that's doing it. And when you ask, we don't know why. It just, at some point things break down and the muscles start to die.
Yeah. So it's actually more optimistic than that. And from my point of view. So in Parkinson's, I believe the experts in human genetics say it's about 85% of the cases, 15% of the cases are known genetic drivers. Yeah. 85% are called sporadic. What's amazing is that the tests of the drug have been done in a bunch of the different known genetic drivers. The human data is presumably, because it's random, is largely the sporadic. The fact is it's working in both. So I actually think, to me, that tells me this is probably the root of it. There may be exceptions, of course.
Right.
We actually found one in this paper that's coming out that one of the initial names for these genes were called PARC genes for Parkinson's. These are attempts in human genetics where you find families and you sequence family members that are affected and you narrow it down to a gene. And for a while, for a 25-year period, they were called the PARC genes, PARCs 1 through 23. Mm. That name isn't used anymore. I don't know why, but PARC 7 is a small molecule. It's a protein called DJ1. And what we discovered, by a little bit of chance, we'd been following a lead that we'd found it was a claim that DJ1 might interact with this enzyme PGK1. And what we discovered is when we remove DJ1, this drug doesn't work anymore. And it actually creates a massive metabolic problem on its own. And the gene therapy doesn't work anymore. So this may be one we can't fix because it's too intimately connected to the problem. I mean, can't fix currently, I should say.
Yeah.
Not with this trick anyway. But it's looking like many of them actually will be. I'm confident they're going to be connected to this. So what I'm hopeful is that even though we don't still understand how the drug works, but we have much higher confidence, I do now, that it's really via this enzyme, perhaps with the partnership of this other Parkinson's gene, And so this is what you need as the toolkit if you want to try and help the world make a better version of the drug.
Yeah.
This would be the starting point. For that reason, I'm excited.
Okay. All right. There's two things I want to ask you.
Yeah.
To finish this off. One is, you just said, when you give talks and stuff. So I think in 2022, you gave a talk at the International...
Brain Energy?
Yes. International Brain Energy Metabolism Conference, right?
Like that,
And then I think 2023, the Korean Society for Brain and Neural Sciences.
Yeah.
And then I think last year, you're elected the National Academy of Sciences, right?
I was.
So my first question is, do you think you're doing the best science of your life now?
Yes.
Huh.
I do.
And so the follow-up is that rare? I mean, I don't know what's the corollary, but I don't know that certainly athletes aren't doing their best work in the last third of their career. And I don't know that Bruce Springsteen's writing the best music in the last third of his career. But for science, even for science, is it rare to be doing, your best work in the last, maybe, I don't know how long you do this, Tim, maybe the last third of your career? I don't know.
It's a tough question to ask. I mean, in physics, there's this old thing of theoretical physics, of course. The problem is there's a few data points of absolutely brilliant contributions from guys in their 20s and 30s.
Yeah.
Right. And you could say, well, Werner Heisenberg and Paul Dirac, their big breakthroughs came roughly at the age of 30, right?
Yeah.
Now, at the same time, it's kind of hard to top what they did. So, there's no way they could do it again. They could do better because those are singular moments.
That's right. Yeah.
In the history of science, right? And so I never liked that example because it doesn't mean that their capacity for doing great stuff changed. It's just that they peaked so damn early.
They found a moment early.
They found a moment early. The example that is often used is, Giuseppe Verdi, great composer, continued composing his most famous operas well into his 80s.
Yeah.
Right?
Yeah.
And so I feel incredibly fortunate that I get to continue to experience the excitement that I did, or very early on when it got me excited about I didn't expect this result. This is, I have to think about this. That's exciting. So I'm really happy that happens today still.
Okay, that's it.
Okay.
Thank you very much. I'm still thinking about the way a discovery lives on, how it is reborn as a new discovery for every single person that learns about it. I love that. So thank you, Tim, for a great talk and for hosting me in your office. Okay, this podcast will be archived on thetransmitter.org, where we have also included a transcript. In the transcript, we have inserted links to some of the papers discussed, so check that out if you'd like more information. This show can be found wherever you get your podcasts: Apple, YouTube, Spotify, or in whatever podcast app you use. Some of the information for our intro came from the website and educational materials for the Fermi National Accelerator Laboratory. If you'd like to comment on this show or whatever we do with the Transmitter, you can find us on the social media platforms X, Mastodon, Blue Sky, and LinkedIn. Our theme song was written and performed by Chris Collinwood. Thank you for listening to Synaptic. Until next time. Tough question, but is it possible
Yeah.
to silence that?
Yeah.
Okay, we will.
I wish I could say yes, but I have no control over it.
That's fine. We'll just we'll get close to the mic so